Hi, everyone. I want to start talking about integration and specifically the fundamental theorem of calculus, this magic trick of like somehow using antiderivatives to find the area under a curve. And I want to motivate why we might think that might work. And I think the best way to motivate it is involving distance and velocity. So in particular, say you're given some velocity data about an object, like basically how fast an object is going at certain moments in time, and you want to estimate how far it's traveled. So as an example, like as a kind of silly example, I mean, you have your speedometer in your car, but let's do something a little more down to earth. Suppose you're walking from Thorn to Searles. So what does Thorn look like? I don't know. It's a tower, right? Tower, dining hall's there. So that's Thorn. And you're going to walk to Searles, which is greatest building on earth. It's the kind of looks like that, sort of. It's one window. And suppose somehow you're carrying a speedometer with you. It's a very contrived situation. And you want to sort of measure how fast you're going at different moments, and then try to use that to estimate the distance. So the distance is sort of unknown. And but let's try to measure your distance. So let me see if I can do that. Here's some data. Oops. Come on. Yeah. So here's some data. Say you measure just at the beginning. What is this? Oh, I see. I've got, oh my God, I have to learn how to make videos again. Okay, I drew on the thing. This is some data I took. Just say at the start, say it takes you 5 minutes. So let's say the time is 5 minutes. The distance is, we don't know, but we have this velocity data. So say when I walk out of Thorn, I look at the speedometer and I'm walking at 60 feet per minute. And that's the moment I walk out of Thorn. And the moment I get into Searles, I'm walking 420 feet per minute. So then, okay, so the question is, what can we do with that information? So can we get some crude estimates of the distance from this information? Some guesses. I mean, right, we don't have very much data, but so can we guesstimate distance from this limited data? And the answer is sure. I mean, we're going to make some assumptions. So one thing you could assume, and it's going to be useful just to think about plotting sort of velocity versus time. So say we have some graph like this, and we have time in minutes on this graph and velocity in feet per minute on the y-axis, time on the x-axis. And so then at t equals 0, you know, we have speed 60. So let's say that's height 60 right there. And at t equals 5, it's at height 420. Right. And okay, well, you could imagine lots of things happening, right, in between the two. So let's just try to imagine what could happen. Like I could do, it could just be that it sort of goes up and I get faster and faster as I go. That's one possibility. I could walk very slowly and then all of a sudden, right, like I just go dashing into Searles at the last second. Or I could walk out of Thorn slowly and then dash and then speed up and start heading towards Searles pretty fast the whole time. You could, I mean, there's really a lot of assumptions here. I could walk for a little while and then just come to a stop and talk to somebody. I don't think the graph is supposed to really double back on itself, but I could stop. I guess it could be like this. Stop for a minute, talk to some people, and then race off to Searles. Well, who knows? but head off to Searles. So there's, we don't know. We don't know what's going to happen in between here. I mean, I could even start walking towards Searles and then realize I left something in Thorn and go backwards and then go forwards again. So, so down here where you have, down here in this area where you have negative velocity, it's, I'd actually be going back towards Thorn, right? So, so anyways, there's just lots of possibilities here. So, okay, long story short, the best estimate we can make is, so one possibility, we could assume we're going 60 feet per second per minute the whole time. I mean, I can run 60 feet per second, but I don't know about you. 60 feet per minute the whole time. And so that would mean that for 5 minutes, we're basically running 60 feet per minute. So that would be something like this. And then maybe, at the very last second, it jumps up to I run in. And so so for 60 feet per minute times 5 minutes, you multiply those two, right? Because distance equals rate times time. And, see how the units cancel out. And so we get feet. And so that would be 300 feet. So that's one crude estimate you could get. A second crude estimate would be just assume you're going, I leave and I speed up to 420 and I go 420 the whole time. So assume 420 feet per minute the whole time. Right, so that would be the same kind of calculation. 420 feet per minute times 5 minutes. I think if you do that, you get 2,100 feet. Okay, so that's a pretty wide, we think probably, if assuming that we just sort of head towards Searles the whole time, we don't really slow down or speed up, outside of the range of 60 to 420, then maybe there's an underestimate of 300 feet, and an overestimate of 2,100 feet. That's a pretty big gap. One thing you could do to make life a little better is you could also average 1 and 2. So 3, we could average 1 and 2. There's nothing wrong with that. And if we do that, what do we get? We get 300 plus 2,100 over 2, which is 2,400 over 2, which is 1,200 feet. So, I mean, this is really not enough data to make a really good guess, but you can sort of get the sense of what's going on here, right? These are at least some possibilities. Okay, so next I'll try to see what happens when we do some more data.